All right, welcome to The Explainer. Today, we are diving deep into probably the ultimate cosmic mystery, right? The point where space, time, and honestly, our entire understanding of physics just seems to break. We're talking about black holes. So let's take a trip to the very edge of reality and see what we can find.
It really all comes down to this one simple but incredibly powerful idea. We're about to explore a concept so extreme it pushes the laws of physics to their absolute limit. A place where gravity, the most familiar force in the cosmos, becomes completely and utterly dominant. It just wins.
But here's the thing. This isn't science fiction. This is a real scientific detective story, one that took over 200 years to solve. And it didn't start with a giant telescope, but with a simple, brilliant thought experiment.
Now, this whole journey took a while. It actually started way back in 1784 with a guy named John Michell asking a question: what if a star was so big and so dense that even light couldn't escape its gravity? Then you fast forward to 1915, and Albert Einstein's theory of general relativity just happens to provide the perfect math to describe these dark stars. But get this, the idea was so weird, so out there that Einstein himself said, "No way, that can't be real." It took until the 1960s for scientists to really come around to the idea and for it to finally get that perfect, catchy name, the black hole.
Okay, so we've got the theory down. But what is a black hole, really? If you could actually look at one up close, what are the fundamental parts? Let's break down its anatomy.
So first up, you've got the most famous part, the event horizon. You have to think of this as the ultimate one-way street. It's not a physical surface you could touch. It's a boundary in space-time itself. The moment you cross it, every single possible path you could take leads in only one direction, inward, toward the center. There is literally no going back.
And at that very center, you have the singularity. This is where things get truly mind-bending. It's the point where all the stuff that made the black hole, maybe a giant star, is crushed into an infinitely small, infinitely dense point. It's a place where the fabric of space-time is so warped that our current laws of physics, they just stop working. The rulebook gets thrown out the window.
And this leads to one of the most elegant and bizarre ideas in all of physics, the no-hair theorem. It's basically cosmic amnesia. It says that no matter what you throw into a black hole, a star, a planet, an entire library filled with information, the black hole forgets everything about it. Once it settles down, you can only measure three things from the outside: its mass, its charge, and its spin. That's it. Everything else about what it used to be is just gone.
So you see the problem, right? This creates a massive challenge for astronomers. If black holes are truly black, if they swallow every bit of light that gets near them, how in the universe do you prove they're even out there? Well, you have to get clever. You have to look for the chaos they create.
The first method is just pure gravitational detective work. For decades, two astronomers, Andrea Ghez and Reinhard Genzel, pointed their telescopes at the very center of our Milky Way galaxy, and they patiently watched as stars there whipped around a single, empty point in space at mind-boggling speeds. They were orbiting something they couldn't see.
Now, by carefully tracking the paths of those stars, they could calculate the mass of the invisible object they were all circling. And the number they got was just staggering. Whatever was there had the mass of 4.3 million of our suns, all crammed into that dark spot. It was an incredible discovery, and it won them the Nobel Prize.
But just watching stars isn't the only way to find them. You know, sometimes the darkest objects in the universe create the most brilliant light shows. See, a black hole itself is dark, sure, but the area right around it can be the exact opposite. As gas and dust get pulled in, they start to swirl around in this cosmic traffic jam called an accretion disk. The friction in that disk heats it up so much that it can outshine entire galaxies. It's like the universe's most violent and brightest fireworks display.
But maybe the most revolutionary method of all isn't about seeing anything. It's about listening. Listening to the silent ripples in the fabric of space-time itself.
On that date, the LIGO Observatory did something for the first time in human history. It detected gravitational waves. These are literal ripples in space-time that Einstein predicted 100 years earlier. And what was the source of these waves? What was the first sound we ever heard from the cosmos this way? It was the cataclysmic collision of two black holes spiraling into each other. It was a brand new way to sense the universe, and it was undeniable proof that these things were real.
So we had seen their gravitational pull, we had heard their cosmic collisions, but there was still one final piece of the puzzle missing. Could we actually take a picture? Could we see the silhouette of the abyss itself?
And this is the moment the invisible was finally made visible. A project called the Event Horizon Telescope linked up radio telescopes from all across the globe, basically creating a virtual telescope the size of planet Earth. And they pointed it at a galaxy called M87. And they did the impossible. They captured the first ever direct image of a black hole's shadow. The theory became a tangible, breathtaking reality.
But here's the beautiful twist in science. Proving that black holes exist didn't end the story. Oh, no. In fact, it just opened up even deeper, more profound questions that push us right to the very edge of what we know about reality.
And this brings us right to the middle of the biggest battle in modern physics, the information loss paradox. Here's the problem. Our two greatest theories of the universe are in a head-to-head conflict. On one side, you have general relativity, which says that anything that falls into a black hole is lost forever. Its information is just erased. On the other side, you have quantum mechanics, which says one of its most fundamental rules is that information can never be destroyed. They can't both be right.
And that leaves us with the ultimate cliffhanger, the biggest unanswered question. When something crosses that event horizon, is its story over? Is its information wiped from the universe for good? Or is there some new, undiscovered piece of physics that we just don't understand yet? Solving that, well, that could be the key to the next great scientific revolution.